frequency h over mv wavelength for a given frequency equals c over frequency. I think I started the other one already. Equals 3.0 times 10 to the 8th divided by 7.30 times 10 to the 14th. (4.11) times 10 to the negative 7th. That's in meters. So to get it into nanometers, because this asked me in nanometers, I got to multiply that by 10 to the 9th nanometers in 1 meter. So that's 411 nanometers. And we just did it by calculating, so it's B. Okay. The wavelength of a particle is given by de Broglie's equation. Wavelength, that's wavelength, equals h over m times v. So it's C. De Broglie equation, which will have the shortest wavelength? The lowest mass will have the lowest wave, the largest mass will have the lowest wavelength. So that would definitely be a planet. Okay, they're just going to ask you to plug in here. So wavelength equals h over mv. So 6.63 times 10 to the negative 34th divided by the mass, which is 9.1 times 10 to the negative 31 kilograms. That's your SI unit. Keep it in there. This is going to be joules. And oh, sorry, they gave me the wavelength, so I'm trying to solve for the velocity. So I'll just rearrange the equation. Velocity equals h over mv. Sorry, m times wavelength. So I'm going to plug the wavelength in down here. 8.7 times 10 to the negative 11th meters. So I got 6.63. It's 10 to the negative 34th divided by 9.1 to the negative 31 divided by 8.7 to the negative 11th. 8.37 times 10 to the 6 meters per second. 8.37 is going to be 8.4. Answer is D. According to the Heisenberg uncertainty principle, it's impossible to know precisely the position and momentum, which is mass with velocity. Direction and velocity. So the answer to that one is momentum, C. That's Heisenberg's uncertainty principle. That's why Schrodinger came up with the idea of orbitals. Okay. Orbitals in the third shell. N squared equals your number of orbitals on that region. And so if you got 3 squared, that's 9 orbitals. You have 1s plus 3 p's plus 5 d's equals 9 orbitals. So the answer to that one is 9. If I ask you for the 4 shell, it's 4 squared, which is 16. They'll add in 7 f's. Okay. Quantum numbers. I don't think I'm really going to give you these type of questions. You have n, l, and m sub l. All you got to know is, do I follow the rules? L has to equal n minus 1 at least. It can't, L and n can't equal each other. Okay, m sub l is plus or minus whatever L is, all whole numbers in between. And then m sub s, the spin if it comes up, is either plus 1/2 or negative 1/2. Okay. As I pile these on, 2, 0, 0 is okay. What does that say? There's an s at level 2, and there is an m sub l at 0. If you have a 1, you can have a negative 1. If you can have a 1, you can have a negative 1. If you have a 1, you can have a 1. If you can have a 2, you can have a 1. Let's look at, I was comparing the m's to the m sub l. These two numbers can't equal the same, or it can't be greater. So 2 and 1, 2 and 0 is good, at least 1 less. 3 and 1, and then 1 and 1, that's not allowed. You have to be at least 1 lower. What this says is, for a p, there are no p's at level 1. Okay? An electron can have which quantum number? 610 is okay. Here's what you can't have. You can have a L of 2, and then m with an m sub l of 3. M sub l has to be plus or minus whatever the L is. So B's your answer. Which one is an incorrect subshell? There are 4 F's at 4. At level 2, there are no D's. So the answer is B. That is to say, here's my D's. They start at 3. You don't see any D's at level 2. There's a hole in the chart right there. They don't exist. Which one feels the most charged? The one closest to the atom. The one closest to the atom would be level 3 and an S. That's the one closest to the nucleus. Which one experiences the least effective nuclear charge? So this one's the closest, and this one is the farthest. The farthest would be in level 5, and it would be a P. A P's farther out than a D. So if I have a P here, first an S, the P's are a little farther out. They stick out a little when they go out further than an S. Acceptable set, N, L. Can't have 2, 2, you can't have 3, 3, and you can't have 3, 3. Negative 1/2, 1/2, 1/2, 1/2. The spin's fine as long as I got 1/2. And then the m sub l is going to be my next answer here. Negative 1, negative 1's okay. 0, 0 is okay. You can't go from a 4 up to a negative 5, so the answer to this is D. 24. I'm ending with 4p3. So here, 4p, 1, 2, 3. It's the atom that's right there, so I want to look at my periodic table, which you always want to have close by. Don't bury it with papers like I just did. So, level 4, P, 1, 2, 3, arsenic. Okay. Which one is the ground state for silver? I'm not going to look at any of these. I'm going to go ahead and look at silver, which is 47. Okay. It's got a noble gas oath. The last noble gas is up and over is krypton. So if it's not krypton, that's not the answer. So it's one of those. Krypton is then followed by the exception, 4s1, and then it fills out 5s1. Then it fills out the 4d, 10, and that lines up to a B. Okay. Try and get through these quick. Okay. Ground state for iron. Iron is equal to, start off with 1s2, 2s2. Here's iron. They give me a full configuration. 1s2, 2s2, 2p6. Go from neon to sodium, that's a 3s2. Go all the way over to the 3p6. Go back to the 4s2. And you end up in 3D. And you count over 1, 2, 3, 4, 5, 6. And that would look like B. That's missing something, that's missing something. And you don't have 4, 4, that's not allowed. So, I just have you draw it out when you do it. Gallium. Gallium's past iron, so I'm going to just repeat everything I did for iron. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and now I'm going to fill out my D, 3d10. Now I go out to the 3d10, that's zinc, and then 1, 2, or just 1, it's gallium. So it ends with a 4p1. So I end up with D as an answer. The ground state of krypton with 5s1 with 4d5. This is an exceptional configuration. You got one electron in the S, and it's still D's up. So start with krypton. It's down in this row, 5s1 and then 1, 2, 3, 4. That's your other exception, that's molybdenum. B. Carbon. Carbon is right there, 1s2, 2s2, 2p2. This one electron is jumped up into an excited state. So when I add my electrons, I still have 2, 4, 6 electrons. 2, 4, 6 electrons. So the answer is A. There are how many unpaired electrons in the ground state of phosphorus? Its configuration is 1s2, 2s2, 2p6, 3s2, and then we ended with 3p3. Right there, 3p3. I actually have to look at the orbital notation for the end. So I got 3s2 and then 1, 2, 3. That shows 3 unpaired electrons. That would be paramagnetic. Anything with unshared electrons and spinning in one direction is paramagnetic. I don't really have to fill these out, but this was 1s2, 2s2, and then p's have 1, 2, 3, and that would have been full. So there's your 4 orbital notation. Which two elements have the same ground state configuration? The answer is no two elements have the same gradient state configuration. This is molybdenum. They gave it to us the other way, and now we're going backwards with it. So here's molybdenum down there, 42. I start with up and over krypton. So molybdenum is everything that krypton has. Now it is exceptional because it's 1, 2, 3, 4 over. It's 5s1 and then 4d5. And again, it took one of the electrons away from the D because it started out with an open P. I'm sorry, an open D. And this electron went into there. So technically that's violating the off-ball principle. But that is the lowest energy configuration for molybdenum. The answer is C. Alright, and that's the review, that's everything. I don't have anything else to show you. Maybe one other thing.